So really briefly, let's talk about nucleophilic aromatic substitution. And there's two ways that we can have these types of reactions. The first one that I want to talk about is called an addition-elimination reaction. And before I go into this, I just want to make a note kind of off to the side here that when you're doing this type of a reaction, that your determining factor, you know, like your priority, I guess, with all this is having W. And a W is a electron withdrawing group. Electron withdrawing group. And the reason why this is so important, I think, will be kind of be self-explanatory when we start drawing out the exact mechanism. But W, when I say that, what I mean by that is this tends to be something that is a meta director. So like a NO2 group would be the perfect thing that you could have for W. But let's just go ahead and draw out our steps. I'm going to try to list them in two steps. The first thing you have is the actual addition. This is of the nucleophile, and then the next step is the elimination, which I hope that'll be kind of self-explanatory. So first thing we have here, and I'm just going to generate it as a, or just kind of redraw it as a generic. It could be any type of a nucleophile. It doesn't really matter the type. And it's going to find itself with some type of an aromatic compound, being benzene is the poster child for it. So let's say that there's a W and then a leaving group. And for a leaving group, I'm just going to say chlorine. Now, if you have W, your electron withdrawing group that's a meta director that is ortho or para to the leaving group, this is going to make your reaction a lot smoother. Let's see if I can clear up that. And that's supposed to be an L. LG to your leaving group. That makes this reaction a lot smoother. So this is going to be a little crazy when you think about it. What I'm going to draw is I'm going to draw this lone pair on the nucleophile. It's going to come in and he's going to attack that carbon there. Holy shit. Like, we're at that point though in chemistry where we're learning how to make reactions proceed that they don't want to do it. Like we're forcing this shit in there, and you're putting electrons. Think about that. You're putting electrons into an extremely electron dense aromatic ring. So I wish that my book would be more specific about how this reaction proceeds, but this is just blows my mind that you're putting electrons on a carbon that's connected to a pi bond. But it does happen. It is possible. So the next step, I'll just kind of draw this out there. And what usually tends to happen, and I don't think I quite thoroughly drew this out, that when you do that, it's not going to stay like that forever. You're going to have pi bonds that are going to jump to the nearby carbon. Now, I've drawn it like this. You could draw it in the other resonance conformer, and it'll be on this end. It doesn't really matter. But the point I'm making is that we jump on to the nearby carbon compound. So I'm just going to go ahead and redraw what we just formed, however unstable it. And really, I feel dirty just drawing it. I don't like it. So that's there. That's my electron withdrawing group. I should have drawn NO2. I don't know why I didn't, but that's my leaving group. And I now have, you're going to get a kick out of this, a carbanion at that point. And so what this carbanion is going to do is it's going to kind of resonate in circles, and then once it gets here, we're going to fling that thing off, if you could think about it that way. But the next step for this is to draw a full-blown resonance structure for this diagram. So carbanion here, it's going to go there. This resonance arrow, this lone pair goes there, and this lone pair goes there. It's getting really messy, but I hope you can kind of see what I'm talking about with this. So end up with that there. W. Chlorine group there. Pi bond there. Pi bond here. and a carbon ion, carbon ion there. And as I guess you can imagine, its next step, it's literally going to go through every single point of here and just knock that leaving group off. But I have to draw the steps that it's going to take. So its next step is to go to this carbon. And in doing so, well, I can't have 4 bonds to this carbon here, so this carbon goes here, and that pi bond goes there. Oh man. And then the next thing, that we get, Cl, there's my NO2, or my electron withdrawing group. The 2, that's my carbon ion there, I have that there. I now have this here. And what's kind of interesting is that the next step is it's literally just going to keep circulating in this. It's very tedious for me to draw. I should have started off at the other end, but oh well, I've already started now. So as you can imagine, there, 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 and I'm just going to draw this going up with it. Just wanted to clarify also that the first step, that's the addition. Everything in around here, we're building up to elimination. So I have my W here, and I have my leaving group there. I believe my carbon ion was at this point. If I am not mistaken, there's that there, and I move that there. There's my negative formal charge there. And as you could expect, we're going to have yet another movement here. So I'm just going to draw this bad boy here, this guy here, carbon ion there. It's a colossal pain to draw these, especially on this pen. Good lord, man, this pen has had better days. There's my Cl. I have a carbon pi bond there, almost there, baby. Okay, so I'm right there. I'm right next to it, next to that point. Here it is. Here's the moment that I just drew all those other stupid reactions for. It literally went from that there. Now we're here. We move this pi bond here, or this electron there, and that leaving group says, I am leaving. I have electrons. I can pull this thing away. We're cool with that, whatever. And, well, obviously I can't have full set of atoms there bound to that, so if you could just imagine me moving these things here, what I'm going to get though out of this reaction, and I hope I'll just draw the product down here. I'll draw it kind of big so you can see where all I moved my pi bonds to, but what I get out of this reaction, there's still my W, my electron withdrawing group, which is good because it kind of like pulls, if you think about it, on this to increase the rate at which or not necessarily to increase the rate, sorry, to increase the, I guess, the amount of electron movement that we're going through here. Because this isn't, I'm not drawing resonance, guys. This is electrons bouncing around and moving things elsewhere. What I'd like to know is why this doesn't just immediately move this one here. But anyways, once we do this reaction, we've now lost that there. We have now moved, I think I drew this pi bond moving here. We have a pi bond there. We have a pi bond there, and we have a pi bond here. And that is my product. That and a chlorine leaving group, which is also a nucleophile, but it's not. I'd assume you need very strong nucleophiles for this reaction, a lot more so than the others. And a thing that I really dislike about my book is it doesn't really say how proficient this reaction is. I don't think your percent yield would be very high with this reaction, but nevertheless, that's how we do this. And so I guess some notes that I wanted to make about this is that in this reaction, your carbon ion will generally, I mean, as it would by any points, the two things that are going to make this stable are the two things that make any carbocation carbon radical stable, and that would be halogens, anything that's going to have an inductive effect, anything that can be inducing, and then of course anything that can be contributing a resonance to the stability of this reaction there. So that's addition elimination. The first thing that happens is the nucleophile adds, and then after this little carbanion bastard is bouncing around, he will eventually move the leaving group off. And so that's how that reaction works. Now, I'm going to see if I can fit at least elimination addition reaction on the same page, just so that you guys can see and compare and contrast the two. But I'll do it in blue. So there are three things that are really, I guess, important to this. So the important factor in this reaction here was that we had a good electron withdrawing group, a meta director, because something that would help us with carbocation stability or carbanion stability of this reaction. So with elimination addition reaction,